Bismillahirrahmanirrahim. Assalamu alaikum, students. In the last lecture, we discussed the Maxwell-Boltzmann distribution of speeds. We talked about the root mean square speed, mean speed, and the most probable speed. We used the partition function and solved for the Maxwell-Boltzmann distribution of speeds expression. Today, we're continuing the discussion of Maxwell-Boltzmann gases. So today, our topic is, let me write it. Our topic today is thermodynamic. Let me write it in another color. Our topic is today thermodynamic properties of a Maxwell-Boltzmann gas. So let us start our topic. Let me get my pen back. This is our today's topic. Let me encircle it like this. Thermodynamic properties of a Maxwell-Boltzmann gas, which is the same as the thermodynamic properties of an ideal gas, which obeys the equation of state PV is equal to RT, where T is the thermodynamic temperature. As we have already established the validity of Maxwell-Boltzmann statistics. So let us move. So first, we will find the expressions for internal energy, and C sub V, which is the heat capacity at constant volume of the gas. So let us denote internal energy by U, and CV is representing here heat capacity at constant volume. Right. Remember, in the last lectures, we have solved for the partition function. Let me write that expression. Z is equal to V times 2 pi m kbt over h square whole raised power 3 by 2. What is this? This is the expression for the partition function for a monoatomic spinless gas. So let me mention it with some other color. For monoatomic spinless gas. So for a monoatomic spinless gas, the partition function is given by this expression. Z is equal to V 2 by m kBt over h square whole raised power 3 by 2. Now we will make use of this expression. Another thing I need to refresh your memory. We know that the U, that is internal energy of the gas, we write as summation J Nj epsilon J. We have already used this notation in the discussion of the distinguishable or localized particles case, and we also have written this expression U by N is summation J epsilon J exponential of beta J, beta epsilon J over summation J exponential of beta epsilon J. Let me check it. Summation J epsilon J exponential beta epsilon J over summation J exponential beta epsilon J. And we know our beta here, we have defined it as minus 1 over kBt. We have discussed this relation, as I told you, in relation to the localized or distinguishable particles case, application of statistical method to localized particles. Now, this equation, we know here, this is Z. Let me use another color. Here, this summation J exponential beta epsilon J is nothing but the partition function Z. So this equation can be written as, we can write it U over N is equal to 1 over Z d by d beta of Z. Check it. This thing in the denominator here is Z. So it is 1 over Z. It's clear. Then when you differentiate Z with respect to beta, you get your numerator. So this expression is same as this. We can rewrite this expression in this form. Now further I can simplify this. I can write it this way. D by d beta of ln Z. Let me name it equation A. And let me encircle it. U by n is 1 over Z d by dz by d beta. It can be, this 1 by z can be absorbed inside the derivative by writing this expression as equal to d ln z by d beta, right? Now this equation A, we have established it by using the expression obtained in the case of localized particles. But this expression depends only on the definition of Z, which is the same for gases as for localized particles. I repeat, this equation A depends only on the definition of Z, which is the same for gases as for localized particles. So we can make use of this equation here also, but we have to take into consideration our Z. We have to take Z, which is valid in our case, but this expression can be used. So therefore I can write U as this here. Let me get my pen. I can write U equaled n times d by d beta of ln z, right? D by d beta of ln z. Now I want to shift from beta to temperature, and beta and temperature are related through this expression. I can write it, I will write directly. I can write it as n kb t square d by dt of ln z. N kb t square times d by dt of ln z. You have to go from beta to temperature transformation. You will see, you will get this, and you will check this at home. I will write here, check it. Now to get the expression for U now, I need to find the ln z. So let us do that. Our ln z is ln of v plus 3 by 2 ln of 2 pi m kb t by h square ln v plus 3 by 2 ln 2 pi m kbt by h square, where we have used our expression for z, which I told you at the start. This I applied ln to this expression, so I got this expression because it is my appropriate z. Now, when I differentiate this with respect to t, I do d by dt of ln z. I will simply get 3 by 2t. Check this. Differentiate it with respect to temperature. It is easy. Check this. So this is my d by dt of ln z, 3 by 2t. So I will plug it into the this expression here. So what I get, substituting in the above equation, let me write complete. In the above equation, we get u is equal to nb, nkb not b, t square times 3 by 2 t, which will be equal to 3 by 2 n kbt. Let me name it equation first. N kbt square times 3 by 2 t, 1 t will go, you will get 3 by 2 n kbt. So we have found, we use it, d by dt of ln are in this expression. So this is my equation 1. So we have found the internal energy of a Maxwell-Boltzmann gas, which is the same as the ideal gas. So let me encircle it in the red color. Let me get my pen back. So this is our internal energy. Now we can see that this is the same result as we can expect from the kinetic theory of gases. Remember, from kinetic theory of gases, we said that the average kinetic energy per molecule of a gas can be written as half m Vrms square which is 3 by 2 kBT. This is the average energy per molecule according to kinetic theory. Now, since the total internal energy is N times epsilon bar, so it will turn out to be 3 by 2 N kBT. So we have got the same relation using the Maxwell-Boltzmann statistics, right? So we need to note that internal energy U for a perfect or ideal gas is a function of temperature only, a function of T only. It does not depend on volume V, right? Now we can easily find from it the CV, that is heat capacity at constant volume, which is simply du by dt. So it will turn out to be simply 3 by 2 N kb. So this is my equation second. Let me encircle it in pink color. This is the required expression for heat capacity at constant volume. As you can see, it is independent of temperature. So let me write it. It is a constant. So according to Maxwell-Boltzmann statistics, the heat capacity at constant volume is a constant. So next we will discuss, we have found the expressions for two things, internal energy and heat capacity at constant volume. Now we will talk about the entropy. For entropy, we will use the statistical definition. Remember, I can write S by Kb is equal to ln sigma. This is the definition. S is the entropy. Sigma is the total number of microstates. Kb is the Boltzmann constant. Then we can approximate it to ln T star. Remember, T star is the maximum value of T, right? Number of microstates. Or you can say it is the number of microstates pertaining to the most probable distribution. We can approximate sigma with T star. So it is our usual approximation, right? Then further what we can do, we have to substitute. Remember the TMB expression. What is that? That is simply product over all groups gi raised power ni over ni factorial. This is our counting principle for Maxwell-Boltzmann statistics. Product over all I groups gi raised power ni divided by ni factorial. So we will put this for our T star. And this is also, this expression is the most probable distribution T. So it is here T star, not just T. So we put it, therefore it becomes ln of product over all I gi raised power ni over ni factorial, right? Using this expression. Then this for ni factorial. Now, by the application of ln, this becomes summation. We have discussed it many times. It is summation I ni ln gi minus ln, let me adjust my pen, minus ln ni factorial. We have applied logarithm. Summation I ni ln gi minus ln ni factorial. Then next step, I write it this way. Let me write it neatly. Summation I ni ln gi minus ni ln ni plus ni. What we have done? We have used Stirling's approximation. So let me specify here. So what is it? It's our S by KB. So using Stirling's approximation. S by KB summation I ni ln gi minus ni ln ni plus ni. Or I can rearrange it. Let me, okay, write the same. I can write it as summation I ni times ln of gi over ni plus 1. Check this. So I've just rearranged the terms. So we got S by KB is summation I ni times ln gi by ni plus 1. So ni is outside, ln gi by ni plus 1. Now we need to find this ln gi by ni and put it here according to Maxwell-Boltzmann statistics. As you know, for Maxwell-Boltzmann, that is MB, statistics, Ni by Gi is Fi, and that is a exponential of minus epsilon I by kbt, which can be written as n by z exponential of minus epsilon I by kt, because A is n by z, right? Therefore, what is Gi by Ni? Simply reciprocal it. It is z by n exponential of epsilon I by kt. And to reciprocal it, you will get z by n exponential of minus epsilon I by kt. Then you take that exponential of minus epsilon I by kt to numerator. Its power becomes positive. That means it becomes exponential epsilon I by kbt, right? So what about the ln of it? So ln of, apply the ln of Gi by Ni. I will write it directly. Ln z minus ln n plus epsilon I by kt. Check this. This is not integral. Let me first use another color. Check it. So when you apply the ln, you will get ln Gi by Ni is ln z minus ln n plus epsilon I by kt. Now we put it in the expression. We put it here, ln Gi by Ni. So when we put it, we get this. I will write it on next page. So we get S by Kb is equal to summation I Ni ln z minus ln n plus epsilon I by kt kbt plus 1. Now, using summation I, Ni is capital Ni, total number of particles in the gas, and summation I, epsilon I, Ni is U, the internal energy. So let me check it. Summation I, Ni times ln z minus ln n plus epsilon I by kbt plus 1. Ni is outside, this whole expression inside. So I should write one bracket here, right? So making use of summation I ni is equal to capital Ni and summation I ni epsilon I is equal to U, it becomes, I will use another color for that. Let me use this color. So I will get S by KB is equal to N ln Z minus N ln N plus U by KBT plus N. Let me check it. N ln Z minus N ln N plus U by KBT plus N, which can be written as N times ln Z minus ln N plus 1 plus U by KBT. N times ln Z minus ln N plus 1 plus U by KBT. Therefore, we have obtained the expression for S. We will take this KB to right hand side. Let me write that on another page in another color. Therefore, S is equal to NKB times ln Z minus ln N plus 1 plus U by T. Let me name it as equation 3. Let me first encircle it with this red color. Let me get my pen back and check this equation. S is equal to NKB times ln Z minus ln N plus 1 plus U by T. Now this result is valid for any Maxwell-Boltzmann gas. Remember, in this proof, we haven't made any specific assumptions with regard to the nature of the gas. So this is valid for any Maxwell-Boltzmann gas, right? Let me check the number of equations. It was our 2, yes, this is our second, and this is our third. Now we will make specific restriction to equation 3. Remember, for the monoatomic spinless gas, we have evaluated Z. I will rewrite that. What is that? V times 2 pi. We have already written it at the start. 2 pi m kBt by h square raised power 3 by 2, and this u is 3 by 2 n kBt. We have showed it. Z is equal to V times 2 pi m kBt by h square whole raised power 3 by 2. U is 3 by 2 n kBt. So if we make use of these two results in equation 3, we will get, I will give you this an expression. So for monoatomic spinless gas making use of Z equal to this and U equal to this, equation 3 reduces to, equation 3 reduces to, it reduces to S is equal to NKB times ln V minus ln N plus 3 by 2 ln T plus S naught. I name it 4, where the entropy constant S naught is given by NKB times 3 by 2 ln 2 pi mkb by h square plus 5/2. Let me name it as equation 5. Let me check these equations. S is nkb times ln V minus ln N plus 3 by 2 ln T plus S naught, where this S naught entropy constant is nkb times 3 by 2 ln 2 pi mkb by h square plus 5 by 2. Let me encircle these equations. So let me get my this. I will encircle this. Then I will open up. I will Now this equation 4, that is the expression for the entropy of a monoatomic siphonless gas, this equation has a name. Let me get my pen back. This equation has a name. It is called Sackur tetrode equation. So to get this equation, that is your homework. Prove it at home. You have to make use of z equal to, that is this expression and this expression, in the general expression for any Maxwell-Boltzmann gas, equation 3, and get the Sackur tetrode equation. So I stop here. Before stopping, I will summarize what we did. So today we were discussing the thermodynamic properties of a Maxwell-Boltzmann gas. So first we found the internal energy and the heat capacity at constant volume, and we saw that our expressions were the same as we obtained using kinetic theory, or as you might have done in your earlier class, the kinetic theory of gases. Then we found the expression for entropy. First, we obtained the expression for entropy for any Maxwell-Boltzmann gas. Then for a specific case, monoatomic siphonless gas, which is the Sackur tetrode equation. So don't forget to like, share, and subscribe my channel. You can have queries. You can comment in the comment box. Thank you. Assalamu alaikum.